clean operations. If particles are less than 25 microns, the equipment is generally operating satisfactorily. Secondly, the larger the particle, the greater the damage, and an increase in the number of particles indicates an increase in the amount of damage. When a sample is abnormal, then send it to an off-site lab to analyze the particle type and determine whether it is a contaminant or actually a wear metal. The most common contaminant is silica, which is sand or dirt, and its crystalline structure is much harder than machinery components, even carbon steel. It is 3 times harder than the case-hardened surface of the races of a rolling element bearing. Since 2/3 of the Earth's crust is covered with silica, it is a very likely contaminant which can enter the system through the breather of the oil sump. When silica is present, wear particles are usually present also. Maintenance personnel must find the source of any contaminants and remove it before it degrades the oil and promotes machine wear. Simply changing the oil may remove the contamination in the system, but if the root cause of the contamination is not removed, it will quickly become contaminated again. Changing the oil when it is not degraded is wasteful. After identifying and removing the source of the contamination, then take the steps to clean your contaminated oil. Wear particles indicate the machine's condition and are measured similar to contaminant particles but are different materials and are usually larger in size. The only time that ferrous material or iron will be in the system is as a result of wear. Ferrous wear can be checked in-house using the 51 FW ferrous wear monitor and works equally well with oil or grease. It is a quick tool requiring only 10 seconds per sample for the vibration analyst to use to detect iron particles and then confirm the problem with a vibration analysis. The 5100 Oil View Analyzer uses electromagnetic separation to detect the presence of ferrous particles on a sensor grid. A microscope can be used to determine the cause and source of these abnormal wear particles. One group of wear particles is caused by a 3-body system. A system typically has a 2-body system, that is, 2 components of a bearing, for instance, are separated by a thin oil film. When a 3rd body, such as dirt or silica, is in the film, it will cause scraping or gouging of the bearing components, creating a long, narrow particle similar to a machining swarf. When this abrasive wear is present, find the source of the abrasion and remove it. Check the breather for possible influx of contaminants and make sure the filter is adequate for the application. Fatigue wear occurs when components have been flexed due to repeated changes in loading and they simply come apart. The root cause may be misalignment or unbalance, but the extra load placed on bearings, shafts, and other components causes separation in the metals. This is the spalling that occurs in bearings or gears, and when examined under a microscope, will be chunky in shape. This fatigue wear should alert you that the components are nearing the end of their life. An anti-wear additive, sometimes called an extreme pressure additive, can be input into the system at this point and may extend the life to a scheduled outage. Laminar particles are similar to plates and may be round or oblong but thin and have parallel lines in one direction. These are from severe sliding or adhesion wear and can be the result of a rub, imbalance, or misalignment. These 3 wear particle types, the abrasive, fatigue, and the adhesion, can be ferrous or non-ferrous metals, although typically 80% of the wear particles are steel or cast iron ferrous particles. Non-ferrous wear metals are copper and copper alloys, chromium, molybdenum, aluminum, lead, tin, silver, nickel, palladium, and titanium. The copper alloys will range in color from salmon pink to brown, with varying shades of yellow. Nickel and chromium will be bright silver in color, while tin, lead, and aluminum will be various shades of gray and white. The particular metals may be difficult to distinguish in on-site capabilities, but you can screen the sample to verify the correct lube. Check for degradation and acidity. Determine the presence of contaminants, including water, processed fluids, and solid particles. And determine the amount and size of wear particles, especially ferrous wear particles. When any of these oil or machine condition indicators are in the abnormal range, send the sample to an off-site lab for further analysis to determine the exact contaminant, wear particle sources, and the condition of the additive package. An off-site oil analysis lab designed especially for handling industrial oil samples, such as CSI's tribology lab, has the equipment and expertise necessary to provide detailed analysis of your lubricants to help you maximize the life of your machines. In your on-site lab, you can detect particles in the oil, but here we can provide the exact molecular makeup and elemental analysis, which can help you determine the source of the contaminants or wear. When a sample arrives at a lab, it is logged into a database, recording any information you provide about the oil, the application, the process, and the equipment, including bearing types, gear types, and its working environment. The sample is then processed through the FTIR, or Fourier Transform Infrared Workstation, to measure the chemistry or molecular structure of the lubricant and contaminants within the lubricant. It uses an infrared light source transmitted through the lubricant film, measuring the absorption of the discrete infrared wavelengths by the fluid. The absorption is due to oxidation, sulfation, nitration, glycol, or water, which each have a particular wavelength. The spectrum is searched for these particular wavelengths and compared with a reference spectrum to determine their presence in the lubricant. This FTIR analysis is performed first with its results pointing to other tests and measurements that should be performed, such as the total acid number or the Karl-Fischer test for water. The sample is then processed through these two capillary viscometers to determine the exact viscosity and analyze the quality of the base stock. The oil is deposited into capillary tubes where the flow is timed after it is heated by the solution to 40 or 100 degrees centigrade temperature. The viscosity is measured in centistokes and then given the corresponding viscosity index. An oil that is extremely different at 40 and 100 degrees centigrade will have a lower viscosity index indicating a lower quality base stock, while an oil whose measurements are fairly close will have a high index number indicating a good base stock. This measure provides extremely accurate information, allowing you to compare it to manufacturers' recommendations and reference samples. The next analysis is the spectrometric oil analyzer, which determines the elements in the oil. Each element emits precise spectral colors when ignited, and by igniting the sample and measuring and separating the wavelengths of color light into the color spectrum, the elements that are present are determined. The well-mixed oil solution is placed in a 1 milliliter bath with a carbon wheel dipping into the bath, bringing it up to another carbon electrode where the oil is energized, igniting the particles. The spectral colors are summed to determine the total amount for each element. The elements are recorded in parts per million for particle sizes less than 10 microns. The tests detect and measure contaminant metals, additive metals, and wear metals. Contaminants such as sodium, potassium, and boron are indicative of coolant leaks, while silicon is from dirt getting into the system. Additive metals in the fluid can indicate the level of degradation by measuring the depletion of the elements that make up the additive package and trending it over the sample periods. Common additive metals are magnesium, calcium, barium, phosphorus, zinc, and sometimes molybdenum. Wear metals detected are iron, chromium, copper, aluminum, molybdenum, lead, tin, nickel, and silver. Because the spectrometric oil analysis does not address particles over 10 microns in size, when any of these wear metals are detected in abnormal amounts, the sample is tested on the ferrous wear analyzer, and then a full wear debris analysis is performed. The wear debris analysis workstation separates iron from other particles in the fluid by using a vibrating magnet separator, and the non-ferrous particles can be poured off and analyzed apart from the ferrous particles using a microscope. The particles are classified by the type of wear material, the actual sizes, shapes, textures, and the average density per square millimeter. The wet chemistry automated workstation measures the total acid number and gives a precise measure of water in the oil using the Karl-Fischer test. It is used when the FTIR analysis indicates oil degradation or that water is present. The TAN of a new lubricant should be 0.0 to 2.0. An increase in acidity by 2 points or 50% indicates there is a real problem with acidity. Water content in a lubricant should be low when the lubricant is new, and goes higher over time due to condensation or leaks in the system. Trending these characteristics from the new lubricant condition provide a picture of water contaminants and oil quality by the presence of acid, indicating the oil may be affected by oxidation, sulfation, and nitration. The lab results can be accessed by your computer via modem for instant access, complementing your on-site analysis, enabling you to make the vital decisions about the life of your machine. A chemical company refused to implement an oil analysis program, claiming that oil analysis did not work. They showed a sample taken from a pump that was sent to an oil lab for analysis. The lab tested the sample and gave it a clean bill of health. Less than a week later, the pump failed. Why did the oil lab give the sample a clean bill of health? Did the sample really have information that would indicate a problem with the machine? The test performed by the lab was a spectrometric oil analysis, which is a good test to determine the elements present in the oil. The results were in the normal range. What went wrong? Remember that earlier we used the analogy of tests performed on blood to determine the illness. A blood sample would not have the same test run for a common cold as tests for cancer. It would not be wise to perform just one test for any condition, but instead, tailor the test for each condition. The spectrometric oil analysis is only able to flash or burn particles that are 10 microns and smaller. When the sample was tested again for large wear particles, it had excessive ferrous fatigue wear chunks in excess of 250 microns. They were so large, they were ignored by the spectrometric oil analyzer. A failure progression typically begins with wear particles in the 10 to 20 micron range, increasing in size and number until failure. Wear particles in the final stages can be in excess of hundreds of microns. Wear particles give the best indication of the severity, but may be overlooked with spectrometric oil analysis. This problem could have been avoided if a plan had been in place to test the oil based on the machine's needs or profile. A profile is a series of oil tests designed for machines with specific characteristics. A turbine, for example, does not have the same lube requirements as a gearbox and should not have the same tests. There are many profiles, but they can be grouped into 4 basic profiles. One is a clean systems profile, which includes turbines, hydraulic systems, machines with sleeve bearings, and extremely critical contamination-sensitive systems. On-site analysis for clean systems should include viscosity, degradation, and particle counting. The laboratory analysis should include spectrometric analysis to test for additives, viscosity index, FTIR to test for molecular degradation and water contamination. Industrial drives such as gearboxes, crushers, chippers, and stamping processes should be tested for ferrous wear and wear debris analysis, as well as checks for viscosity, water, and other contaminants. Off-site analysis should include a full wear debris analysis, viscosity, water contamination, spectrometric oil analysis for the additive condition, and the FTIR to determine degradation. The industrial preventive profile includes common pumps, fans, compressors, and engines. Tests should include all measurements the 5100 analyzer performs for contamination, degradation, and wear. The lab test should be the FTIR, the viscometer, spectrometric oil analyzer, and the ferrous wear monitor. The last profile is grease, which should be tested in-house with a ferrous wear monitor. Lab tests should include a wear debris analysis, ferrous wear index, and spectrometric oil analysis. All machines are not the same, and all oil tests should not be the same. And just like vibration alarm levels are unique for each machine, the oil quality levels and cleanliness levels are unique for each profile and machine type within a profile. Standard machinery guidelines are usually provided by the original equipment manufacturer, the oil analysis laboratories, and the lubricant supplier. These sources provide good starting guidelines, but just like vibration alarm levels, they must be tailored to the machine based on oil trending, target cleanliness levels, and the maintenance philosophy of your plant. Earlier we showed the oil analysis loop and pointed out the need for a plan before any benefits can be realized from a complete tribology program. The plan must identify the critical machine, the profiles, and the alarms, along with a goal of desired results and a training program to qualify all personnel involved. The main program loop samples at regular intervals, screening them for abnormal conditions, and sends the abnormal samples to an off-site lab for further analysis, while OK samples are stored on-site, with the data stored in a database for comparison and trending with other predictive maintenance technologies. Now you can see the data and plug the information into a computerized maintenance management system, schedule maintenance actions for the machine, and generate management reports documenting the increased reliability, improved quality of the lubricants, and the reduced lube procurement and disposal costs. Completing this loop with the plan and results in place means that your data, including the old data, is working for you, enabling you to have a reliability-based maintenance program. As you implement your oil analysis program, there are a few things you should remember that will help your oil analysis program have immediate successes. First, if a machine failure occurs, thoroughly clean out all wear debris before refilling the system. If it is not cleaned out and flushed, the wear debris will quickly cause another failure. Observe how oilers handle the oil for the various applications. Many times the wrong oil was used because it was closest, and the oiler did not realize the severity of using a different oil. Proper training can help avoid this common problem. If you have a product performance problem, check that the product in storage is protected from dirt and water. Also check the apparatus used to transfer the oil. Look for an outside problem before looking at the oil. Eyeball the sample before you send it to the lab. If the sample looks milky, water is present. If you have foam, ask if a defoamant has been added. Foam does not lubricate well, but gearboxes tend to whip the oil into a frothy foam, causing air entrainment. In other words, visually inspect the sample and use common sense. Do not be too quick to blame the oil or grease in an oil-related problem. Look for outside sources of contamination and adverse operating conditions. Always use clean sample containers. Resample to ensure a representative sample. These troubleshooting tips seemed obvious, but are sometimes automatically ruled out because they're obscured by the pressures of providing a fix to the current problem. While many areas have been covered, we've only highlighted the most common oil analysis practices and characteristics. We realize that unique design and applications necessitate special considerations for oil analysis programs. Thank you for joining the thousands who have recognized CSI training as leading industry with quality information, instruction, and application of PDM and RBM techniques and products. Whether your plant currently uses preventive, predictive, or proactive maintenance practices, we're confident that the application of these tips and techniques will help you succeed in your oil analysis program. We look forward to assisting you achieve success in your future endeavors.